Okay, Assalamualaikum and good morning. So we'll continue with our lecture today. Suppose that's it. So let's continue where we have. So can you see the slides or the notes? Okay. So yesterday, what we did was to consider, for example, electrodynamics, which was essentially left out from Galilean relativity. Okay? So Galilean relativity merely considers mechanical systems for which you use, in fact, your definition of inertial frames uses the Newtonian laws of what you call equations of motion. Okay, so in that sense, it's left out one branch of physics at that point in time, which is known to physicists or scientists, which is electrodynamics. Okay, so we have mentioned about idea of light, which are essentially part of no, visible light. I mean, which is part of the electromagnetic wave spectrum, and they consist of oscillations of electric and magnetic fields propagating at speed of light. And the speed of light itself is essentially finite, so it's not infinite. So you are not able to send instantaneous signals to observers or from other sources. Okay, so that essentially explains quite a few phenomena. So today we're going to look into the theory that describes the electric and magnetic fields, and from I think from, I'm not sure where you have learned this. Essentially, should be in electromagnetism. So you have learned Coulomb's law, Faraday's law for electric fields, and Gauss' law and Ampere's law for your magnetic fields. Okay, and you can see that on the what you call on this left side of these equations, you can see that your electric field and magnetic field are somewhat connected to each other. Okay, and that tells us something. When something is connected to each other, they might be part of a single entity. Okay, and essentially that's what we're going to do in special relativity. Okay, so over here you have this is what we call the divergence equation, which is the source. It doesn't involve the source in some sense, and over here it sort of tells you about the source. Okay, we will get to that part of the equations later on, especially much later. Okay, so and then you have this idea of I think this is called electric permittivity or something like that. Okay, and then this is the magnetic permeability. Okay, so this epsilon naught and mu naught, the subscript naught, essentially tells us that is referring to the vacuum. Okay, so when you multiply these two quantity together, it actually gives you the essentially related to the speed of light. Okay, so it's the reciprocal of the square root of that product. Okay, and what we'll do, since we know that these two fields are going to be connected to each other, so what we can actually try to do is to look at this right side of these equations, and then take the curl of the two equations. So in this case, we have curl of E, and once you have that, you will also have curl of B on the other side, and curl of B is basically related to derivative of the time derivative of your electric field. So you get this second order time derivative. Okay. Similarly, you can do that for your case of the curl of B here. So you take the curl of B. Somebody coming in? Uh, curl of B. So meaning you take the curl of partial E partial T, or you can bring in your curl what you call in front of partial T there, and then you'll be able to get the second order derivative of the magnetic field coming from this equation. So you can see that what you have in the end is this equation del cross E equals to something which is proportional to this second order time derivative. Okay, and similarly for your magnetic field. So the curl of something of a vector field, this is one of the things that we can actually do using the index notation. You can see that we have done that earlier, and this corresponds in this particular case the del cross V, del of divergence of V, and then your del squared of V. Okay, so it's just I think in the earlier case we had A cross B cross C, but here basically you have your del. You can still think of it as a vector, okay, vector of derivative operators, and then you can similarly use the identity we had seen before. Okay, so I'll leave that. So I can, maybe I should write that. So, oops. Let me get this done. So you can try to do this as an exercise. Okay. So once you do this, you'll be able to derive the following equations, which is essentially what we call a wave equation for both electric field and magnetic field in the vacuum. Okay, I should say that. Okay, so essentially what you have is the idea of the electric fields sort of obeying some wave properties. So essentially you see that your electric field and magnetic field sort of oscillating to each other. Okay, and this electromagnetic fields, the combination of electric field and magnetic field oscillation propagates with this this is essentially 1 over the speed squared of the wave. So in this case, the speed corresponds to essentially your speed of light. Okay. So that is essentially another part was of classical physics that was missing from the definition of Galilean relativity. Okay, so if you try to simply apply Galilean transformation to the wave equation, for example, let's suppose that you consider the light is actually propagating in a moving frame, say moving frame with velocity v. Okay, so under this Galilean transformation or Galilean vector addition, your wave equation is going to transform into this particular equation over here, where your speed is now replaced by c plus v, where v is the velocity of the moving frame. Of course, you do not see this experimentally. At that point in time, they try to test this, and we will talk about that experiment in a minute. Okay, but the idea there, if you think about waves in general, in those days, they always thought that those waves are going to be propagating in some medium. For example, water waves, you have your water molecules doing the oscillatory motion. Okay, so in those days, electromagnetic waves are thought to be moving in some medium, and that medium is called ether. Okay, and the frame of ether is somewhat what you call considered the preferred frame of the electromagnetic waves, so that you obey Maxwell equation. Otherwise, you might have some modification to the speed over here. Okay. Right. So once you have this idea of electromagnetic waves is sort of moving in the ether, so one can actually talk of trying to see whether there are changes with respect to the speed of your electromagnetic waves with respect to the ether frame. Okay, so the ether frame is one inertial frame, and then you might want to see how this ether frame is probably applying relativity to that, and you see from the point of view of a different frame. Okay, so there's a possibility of detection from that point of view. Okay. So they try to do the experiment. For example, this is the Michelson-Morley experiment. I believe some of you might have learned about this. Did you do this in modern physics? Anyone? Say yes or no. From time to time, I have to check whether you are around or not. Okay, I suppose yes. Right. So the idea is to set up some kind of an interferometer with a light source. So you have this two arms of your interferometer, and there's a beam splitter or a partially silver, partial silver mirror. Okay, for which you allow your light to pass through, but it also can reflect. Okay, so you can see that, okay, once you have this both reflections from one mirror here and another mirror here, then you might be able to see some kind of interference pattern. Okay, so let's consider, for example, the horizontal and vertical arms of the interferometer are of the same length. Okay, but one of the direction, horizontal or vertical, might be moving with respect to the ether. And in this particular case, we will consider the case of the moment with respect to the ether frame, okay, along the horizontal arm. Okay. So, and we consider that the ether frame is moving with respect to the interferometer's frame. Okay, so the ether, you remember the ether frame is where Maxwell equation is valid. That means it propagates with the speed of light. But from the point of view, the interferometer's frame, you will have an additional velocity v. Okay, that might influence the speed of light. Okay, so before reflection at mirror M2 here, okay, M2 is actually this mirror that reflects the horizontal beam. Okay, before reflection, sort of has this light speed c minus v. Okay, because it's sort of the v is essentially the velocity of the interferometer frame with respect to the ether. Okay, so this is c minus v, and then when it reflects, it goes along with the velocity. So or you can think of it as c minus v. Okay, so then you get your light speed to be c plus v. Okay, so you can try to call, find the time that it travels along the horizontal arm. So this will be, no, it travels to the horizontal arm this way, and then it travels back. So you have to consider 2L what I call of path over here, but the traveling to the mirror will have a different speed. Traveling away from the mirror will have a different speed. So you have this time given by this distance divided by velocity here. Okay, L over c minus v is going towards the mirror, and L divided by c plus v is going away from the mirror. So you can do some algebra there, and then you will find out, okay, the travel time along the horizontal arm is going to be given by 2LC over c squared minus v squared. You can divide by c top and bottom, and then you'll find that this gives you this factor here. Okay. So this is the distance divided by c multiplied by this factor. Okay. And then you can try to also look at the case of the vertical arm. So the case of the vertical arm, you have to remember that the frame is actually moving with some velocity v, and because of that, it has this what we call velocity, the effective velocity of the light, okay, given by this quantity, which is coming from just Pythagoras theorem. Okay, and essentially the vertical velocity here has to be perpendicular to the ether frame, so that's why it has to be in this manner. Okay, so and then you calculate the time travel along the vertical arm. Okay, so essentially it gets you this particular quantity, and you can see it's slightly different. Well, I mean, it's different from the one for the horizontal arm compared with the vertical arm. Okay, so you take the time difference between the two. So you get this quantity, which is from the horizontal arm, and this quantity from the vertical arm. Okay, so what we can actually try to do, you have this factor here, essentially 1 minus v squared on c squared minus 1 minus 1 minus v squared on c squared minus a half. Now what we can try to do is to consider the possibility of this quantity v over c to be very small. Okay, and then you can actually do an expansion of the power. Okay, and you can approximate it to first order, which is given by that. Okay, so you just plug in the formula inside this difference, and you'll get your delta t to be equals to that. Okay, and essentially then you can find out what is the optical path difference. So the optical path difference will be given by c delta t, okay, where delta t is given by that. Okay. So in other words, if when one detect things inside an interferometer, normally you look at the phase difference between the two paths. Okay, so the phase difference is given by your delta x, okay, which is your what you call optical path difference here, divided by the wavelength of the light. Okay, so you'll find that this is given by this quantity over here. Okay, and this you can see that, okay, what is going to be v, what's going to be, well, c is going to be speed of light according to the Maxwell equation, and L will be your interferometer arm. Okay, so one can make estimates. For example, the v can think of the velocity of Earth, okay, or speed of Earth, okay, which is sort of different from using that. Excuse me. Sorry, I have to attend to my cats. uh, where are we? Okay, so essentially we have your V to be your, no, essentially your frame of the Earth. So the estimate for the frame of the Earth is given by the Earth speed, okay, which is roughly about that. And then you have to know also what the wavelength of the light. So you take, roughly about 500 nanometers, and your L should be quite at least a sufficient length, which is 11 meters over here. And then you find that your phase difference will be 0.4, and you can actually detect this kind of changes in the fringes of okay. So when they did this experiment, there are no shift of the fringes, and that implies either the following. Excuse me, again, sorry, I have to. Sorry about that. Okay. The absence of fringes, shift of fringes, tells us either the ether is dragged along with the Earth, okay, which is defeats the purpose of the idea of ether frame in that sense. So this is usually not favored, or the possibility of your rigid bodies, meaning the interferometer, this particular case, contract and then clock slow down. Again, this is in some way is not really favored. Okay, so there is another possibility which is actually favored by Einstein, saying that there is no such thing as the ether frame. Okay, now actually these two is quite related to each other. Okay, so the idea of no ether frame in a way sort of becomes a simpler option in comparison with the idea of a rigid bodies contract and the clock slow down. We do have this phenomenon later on when we consider relativity, okay? But that contraction is only with respect to a certain frame of reference. Okay? So this, no, we're going to go a little bit into the formulation of those. Okay? So, okay. So that leaves us, okay, the option of having no ether frame. So to say that there's no ether frame, then that means your Maxwell equation has to be obeyed in all inertial frames. Okay, so that's the basic change that you're going to have. So previously our inertial frame are just referring to your Newtonian's equation of motion. So now we have this extra law of physics that has to be taken into account. Okay, meaning it has to also say that electrodynamics in inertial frames are going to be the same for all possible inertial frames. Okay, So we have now essentially two basic postulates of your special relativity. The first postulate is essentially what we call the principle of relativity, that laws of, in this case there's some qualifier there, laws of non-gravitational physics assume the same form in all inertial reference frames. In that sense, it also includes the Newtonian laws as well as the electrodynamics law. Okay. Another way of saying this is to say that all inertial observers, all inertial observers, meaning observers within the inertial frames, are all equivalent. There's no different from one frame with another frame. Okay. The other thing is the idea of constancy of your speed of light. Okay, and this essentially is tied up to this the first postulate in some sense, saying that the speed of light in vacuum has the same value for all inertial frames. So in a way, that is just a statement of your Maxwell equations must be observed for the electromagnetic waves, and it obeys that the speed of electromagnetic waves in all inertial frames will be this constant. Okay, so that sort of changes the view of what an inertial frame is supposed to be. Okay, so in order for us to analyze further what's the consequence of these two postulates, we need to think of, what is available to a particular observer when they do measurements. Okay, so the best way to think about this is that every inertial observer will be equipped with a standard clock. Okay, so this is sort of measuring the time, and then for length, okay, for spatial degrees of freedom, the observer is actually equipped with light signals. So there will be a source for which the observer can emit a beam of light to some event. Okay, and then it can also receive the light signals from that event to the observer itself. Okay, so in this way, since light signals are going to have the same speed, so the measurement of distance is in a sense standard using the light signal. Okay. The other thing which is probably a bit more intrinsic is the idea of orthogonality of your rods, okay, for which you actually measure the direction of your light signal. So that, in other words, you need to know where is the direction of the light signals emitting and being received by the observer. Okay, so that is essentially what we are going to assume when we do analysis of observers in some inertial frames. Okay, so given that that one of the postulates says that you should have your speed of light to be constant, let's make it a bit easier for us to do what we call analysis by adopting a particular unit where c is actually equals to 1. Okay, in this way, if you think what actually happens in this particular case when you do, say, dimensional analysis, okay, when c equals to 1 being a constant, remember that I should do this here. In the ordinary context, this is going to be LT minus 1, the length, times the inverse time because it's a speed. But if it's equals to 1, and 1 here is being the dimension here, okay, dimensionless. So that will actually implies that L is going to be equals to T. Okay. In some way, this is actually quite nice in a sense that there is no difference between the spatial degrees of freedom and the temporal degrees of freedom, which is the time. Okay, so you put both length and time to be on equal footing. Okay. The other benefit of this, this is sometimes called, when we adopt this is sometimes called the relativistic units. In fact, in theoretical physics, we sometimes adopt what is said to be natural units. Just for your information here, natural units also adopt another constant to be equals to 1. So first is C equals to 1. The other one is H bar equals to 1. So H bar, if we have done quantum mechanics, H bar appears there. Okay. So analysis sometimes is done in theoretical physics using natural units. So the other thing, the other thing that I should have mentioned is the fact that when C equals to 1, that means your light signals are going to be represented by a straight line with an equal slope, okay, meaning 45 degrees, okay, pi over 4. So so it's this particular line, for example, is a light signal going from this point in time, okay, at the origin of X, for example. This is a two-dimensional case where you have only one dimension X, one dimension time. So you have this emitting a signal to P, and then P reflects that signal back to the observer at the time T2. Okay. So this is the idea here is this slope, okay, it's always 45 degrees, or slope 1 or slope minus 1. So minus 1 here is the fact that this emits back to the observer, okay, over here. So basically, if you think about this, it's like X equals to plus or minus T. Okay. So there is this possibility of having the minus sign because you have directions. Here one direction, here's another direction. Okay. And with these light beams, one can actually coordinatize this event, whatever this event is supposed to be. Okay. So you can consider, for example, the time coordinate for this P is given by, since you have a clock, you can measure what this time is going to be. This is T1 and this is T2, and then this is just an isosceles triangle. So you actually have that this time, okay, which is that time, is going to be half times the sum of T1 plus T2. Okay. And the distance, okay, will be simply just the speed of light, which is constant, times the time difference, T2 minus T1. Okay. And this has to work in all frames. So here is one possible frame. Essentially, I can think on an observer here at rest. So the observer just traces out this axis in time, okay, because the observer here doesn't move. But you can also do this for any other frames, okay? And we'll see that in a few minutes. Okay. So okay, so as I said, the light signal will always be inclined to uh, 45 degrees in all frames, and this is essentially the application of principle of relativity. Okay. Generally, we should have other particles beside light. Okay, light are just one type of particles, photons. Okay, for other particles, then they might trace a different path. Okay? For example, here's light, then a particle might just have, sorry. So the light, remember, it always have this 45 degrees. Other particles will have a steeper slope in this case, because time is going this way. Okay, so other particles will have slope which is greater than 1. Okay, because other particles will have speed less than the speed of light. Okay, one could hypothesize a particle which is greater than speed of light, and this actually causes problems in terms of causality. So you can actually use those type of particles to violate causality. But maybe we'll do this at some other time. Okay. And this whirl line, so this is a whirl line of a photon. We call that the trace of this path made by photons, okay, as whirl line. So this is a whirl line of photons, and this will be a whirl line of other particles. And a free particle will always trace out a straight line. If the particle is actually having under the influence of a force, then basically what you're going to get, you'll probably get a curve. So this is a free. So there's a curve there. So this is a whirl line of particle under some force. Okay. So so we analyze all these whirl lines accordingly. Later on, we'll talk about kinematics once we have set up all the tools for special relativity. Okay. So one should here is a cautionary note. This is just like the case of a one-dimensional spatial degrees of freedom. So there's only x, but in 3 dimensions there is a problem of orientation. So normally what we'll do is to fix the orientation, we would like to have your axis carried by an observer to be non-rotating, to simplify what we call the analysis. Okay, so it's always fixed in a particular direction. Okay, so once you have that, okay, then an emitted signal will have this what we call a direction cosine. So this is cos theta 1, which is with respect to the, it's like projection, okay? Projection to the x-axis, cos theta 2, projection to the y-axis, cos theta 3, projection to the z-axis, okay? And for received signal, so this is emitted in this way. So you emit and then receive. So it's going to have an opposite orientation, so it has a minus sign instead. Okay. So once you have fixed the orientation, then you'll be able to coordinatize the spatial coordinates in this way. Okay. So dp would be the length that the length of that, well, it's not, that is the spatial length of that event P earlier, okay? And then you just multiply with the direction cosines, then you get the coordinatized spatial coordinate, okay? And beside the spatial case, we also put in time. So now we are going to coordinatize space and time together, okay? So you have your spatial coordinates, and then the fourth coordinate will be time. Okay? So let's see what's going to happen when you do some kind of analysis with respect to this kind of diagrams, so to speak. So you consider, for example, another observer, okay, moving with some velocity v in the x direction. So my x direction is actually the horizontal, okay? This is time. So your O in this case will be stationary, but then if you have your O dash, the other observer, which has a different inertial frame, O observes O dash to be moving, so it has to move in some direction here. So that corresponds to the velocity of the this slope will be the inverse of the velocity. Okay. So you have this slope for O dash, saying that, okay, my spatial position of the O dash with respect to O will be different time-wise, okay? So that means this observer is actually traveling with some velocity here. So I can start coordinatizing some event P here. So for example, event P is actually here on the world line of O dash, okay? Then I can coordinatize P relative to O dash, okay? And relative to O dash, so I have, how should I say it? Okay, let me just say that your time axis, your t axis, is actually your x equals 0, right? This is for O. Okay, then you get this time axis. Okay, remember that x-axis is here, and then essentially your observer O doesn't move, so it just propagates in time along the time axis. Okay, your position is always at the origin. But the same thing with respect to O dash, okay? According to O dash, despite it's actually moving with respect to O, in O dash perspective, he is essentially, or she, okay, to be politically correct, he or she, according to he or she, is not moving. Okay, in the frame of O dash, he says O is moving. So in other words, the t dash axis for O dash is again x dash equals 0. I hope everyone understand that. So in other words, the coordinates of P relative to O dash would be just 0, 0, 0, okay, and then T dash. Whatever that time is going to be. And then for coordinates of P, this event, okay, will be your spatial coordinates, okay, the one like we have mentioned earlier, and then the time of P. So we can start doing all this analysis using these diagrams quite easily. Okay. Okay. So there are now actually two different perspectives. So I'm drawing here as if is O is actually stationary and O dash is moving. So this is in the frame of reference of O, but one could have the other way as well. So you have your O dash is not moving, and then O is actually moving. So in other words, we have this idea of a kind of symmetry between these two inertial frames. Okay. The only difference here in the case of O dash, you will see O to be moving in the negative direction. Okay, so probably the picture will be something like this. This is O dash, and then O will be oops, not doing. Not good at drawing here. Oops. Okay, never mind. So this is O dash. Sorry, this is O, and this is O dash. Okay. So that will be the other perspective. Okay. How are we going to compare between the two different frames? Because they use different coordinates, and we need to have some kind of a transformation law between these coordinates. So that's the next thing that we want to do, and it's okay. The fact that we are using diagrams, it's nice to have a kind of a calculus that translates from one frame to the other frame, and this calculus is known as K calculus. Okay. So how we are going to coordinatize, for example, the time. So what an observer can do is to send out light signals at some regular intervals. Okay, so it gives you a pulse of light at one time, and another pulse of light at another time, and then you have a regular repetition of those pulse of lights, and then they can start to coordinatize those events. Okay, so O dash on its on his part, if O is sending the light signals, O dash will be receiving at the light signals at some regular intervals. Okay? And that's the fact that this might have slightly different what I call time intervals because of the finiteness of your velocity of light. So they may actually have different what I call intervals over here, and let's call the difference between this interval and this interval is just a factor of k. Okay, so we write in other words we write t dash to be equals to some constant of proportionality k times t. Now what can also happen is that O dash, after receiving the light, will start to emit another pulse of light from O dash going to O. Okay, so the fact that in this particular case, you'll find that because of the symmetry that we have from the different observers, the time difference is going to be just since t dash equals to kt, okay, your t double dash, which is the time it receives, must be just again the same proportionality coming here, okay, because of the symmetry. So now the t double dash is going to be kt dash, but t dash itself equals to kt. So in other words, t double dash is going to be k squared t. So let's do this in the O frame. So what's going to have that event when it receives the light and then send back another light pulse, then that event will have this coordinate, as we have seen earlier, this is your earlier T1 and T2 here. So this will be T plus T double dash here. But T double dash is going to be related to T by the factor of K squared. So I can write down that Tp is just half times 1 plus K squared times T. And then for the spatial coordinates, it's just, remember, is the difference between the two events, T2 minus T1, okay? When it receives the light signal, receive and send the light signal. So this is the receiver part, this is the emitting part. So this is now T double dash, and this is T, and that gives you a K squared minus 1 times T. Okay, and for the spatial part, you have to multiply by C. But however, you also want the fact that the velocity of O dash with respect to O is going to be some velocity V, as we mentioned earlier. So in other words, this dP over Tp should be equals to V. Okay, but then what is dP over Tp from this formula is going to be equals to this factor times C. Okay, so just rearranging this equation. So I bring in my C on the other side, so I get V over C equals to K squared minus 1 divided by K squared plus C. Okay, and then one can actually try to solve for what K is supposed to be, and then I'll be able to, just rearranging algebraically, then I should be able to see that the K factor that we wanted was essentially square root of 1 plus V over C divided by 1 minus V over C, okay, coming from this equation. So I'll leave this for you to do the details. So this is an exercise. Okay. One of the things that sometimes what we want to do is to rearrange the factors so that you get this factor of square root here. This factor of square root here is going to be important. This is what we call beta in the future. So sometimes it's written as 1 plus V over C, or no, this is not beta, this is gamma. So, gamma will be this factor of 1 squared minus V squared. So you get this gamma times 1 plus V over C. Okay. Right. Let me just finish this off. So the other possibility now is to actually re-express your time coordinate of that event Tp in terms of T dash. Okay. So T dash is the time coordinate of P according to O dash. So one can actually do the following. Your T double dash, remember, is related to T dash earlier. Let me go back earlier. T double dash is equals to KT dash. Okay. And then your T here is also going to be related to T dash from this equation. Okay, this equation. So one can put this together. Okay, so I get KT dash plus 1 over KT dash, or I can have K plus 1 over K times T dash, which gives you this particular addition of these factors here. And this is actually, you can simplify this, and that gives you a t dash over 1, t dash over square root of 1 minus v squared on c squared. Now, what is this quantity here? This quantity says, okay, the fact that v is always less than c, okay, you'll find that 1 minus v on c squared, is going to be less than 1. Okay, so in other words, what do we have over here? This t dash is going to be divided by a number smaller than 1, or essentially whatever this quantity is going to be greater than t dash. So remember, again, this is one of the always the confusing part of special relativity. You have to be aware of the meaning of each symbol. Your t dash is essentially what is measured in your O dash frame. This one is what being measured in your O frame, given from TP here. Okay, so this is the quantity that is measured by O. This is quantity what is measured by O dash. And what does it say? It says that, okay, according to O, the clocks that sort of, remember this pulse of light being emitted and then reflected back to O, it's actually the how should I say, the regular intervals in some ways is actually slower than what is measured by O dash. Okay, so in other words, okay, that tells us about the clock of O dash is going to be registering a slower time compared to what is registered by O. Okay, so this is essentially the phenomenon that you have seen before. I hope in modern physics, this is what we call the time dilation. So this is just what we normally say, moving clocks are slower. Okay. So that is probably one thing that we can get from the analysis of these so-called diagrams. Okay, one could actually try to do a little bit more by considering a much more general situation where you have another event which is given by P here, and this event P is not on the what you call world line of this O dash. It's somewhere in between. Okay, previously your P was somewhere here, for example. Okay, then you'll find that, okay, according to O dash, then your spatial coordinate is just 0, 0, 0, and then you have some T dash. Okay, so this is only a special case when the event is on the world line of O dash. So we want to do something a bit different, so that once you do something different like this one, then you actually can compare the spatial coordinates. Okay. So let me go down. Are there any questions at this stage? Maybe I should see if my students are still there or not. Any questions?
Not yet, Doctor.
Yeah. Okay, it takes time to digest this. So probably once you the notes are there on Putra Blast, so you can actually try to what are the things that uh, it's not really understood. So it's usually it's quite tricky when you have to think in terms of two different frames. Okay, so let's look at this. Okay, so let's consider events now. So here you have four different events: A, B, five different events: A dash, B dash, and also your P. Okay, so let's look at event A dash. Okay, so this will be just the same like previously. Okay, so your spatial coordinates according to O dash, okay, will be 0. Okay, and the time coordinate, it's going to be a bit tricky here. The time coordinate is going to be given by it's like this diagram, but now you have it for O dash here. So this is T dash, and then you look at event P here. Okay, so this is event P, and then you really want to find what this time coordinate here. Okay. So the time coordinate here will be this distance. Let's see. Okay, that should essentially I need to find out that that distance over here. Okay, so that you have to look at. Let me try to think about it. This is D dash minus D dash C. So yeah, so in other words, let me go back. I'm just trying to make sure that I did the right thing here. So your D, yeah. Okay, 5 minutes. Right. Okay, let me figure out this thing, and then we'll come back in 5 minutes. Can we restart? Okay, so I'm trying to retrace back how we did this, but probably I will fumble a little bit. But the idea is now I'm going to coordinatize this event A dash, okay, and what I'm going to use is only this parameter T dash, which we know from earlier is going to be half TA dash plus TB dash, okay. So it corresponds to this picture that we had earlier for O frame earlier, how we coordinatize, but now you're thinking of O dash instead. So we have this possibility of looking at this D dash and T dash, and that has to be related to this TA dash and TB dash. Now, if I were to do it now, probably I would fumble, but the idea is just like taking this coordinate of P is going to be what? It's going to be T dash, and then this is going to be T dash. So it's sort of okay. It will be a time which is earlier than T dash, which is TA dash here. Okay, and because of that, this is going to be earlier than that, it has to be subtracted. Okay, and that subtracted is given by this, that amount being subtracted is essentially given by d dash over c. Okay, so I'll let you explore this rather than me explaining here. No, because I know one takes a little bit of time to essentially you need all this information. So essentially you should be able to get this to be d dash minus d dash over c, which tells us this is going to be earlier at this point compared to this point. Okay. If you have problem with it, we can go through this later on. I try not to waste too much time on the algebra, but you should be able to do it. So you just simply look at the earlier what you call parameterization of the time event p, and then relate back to a dash and b dash. Okay. So let's take that for granted at the moment. So you have all this spatial coordinate to be 0 because it's actually on this line. Okay, so it's all 0. So that means the spatial coordinate for a dash will be just the spatial origin of your observer o dash. Okay, so this is according to o dash. So this is at the origin of o dash. Okay. So now we want to do the same thing for a dash with respect to the event a. Sorry, the event of a dash according to o dash is that the event of a dash according to o will have this time coordinate here. Okay, this is just like before. Okay, but now I've already inserted the k factor in, and for the spatial coordinate will be just the velocity of the frame of o dash, okay, times t, which is that quantity, and then we have essentially this will be the spatial coordinate for that event a dash. Okay, so then putting this all together, and let's assume that the direction of the velocity v is simply just 0, 0, v. So this is the vector v. Oh, sorry, not that. I mean is velocity v is just v 0, 0. So there's no for velocity v in the direction y and z is actually 0. So then we can actually coordinatize the whole spatial thing is given by that coming from here, and then your y coordinate for a dash is 0, and z coordinate for a dash is also 0, and then this is the time coordinate for a dash. Okay, and one do the same thing for the case of your b dash. Okay, so you will have just more or less the same thing, but now what happens is that in the case of o dash, it says that okay, the x coordinate of this is a bit funny. Let me think. Sorry about this. This is going to be just like a similar thing like the one we had before. This one. So this will actually happen at some later time over here. So it will be t dash plus d over c. I'm a bit confused. Why is this there? Let me just think. Sorry, I'm looking at a different thing down here. Sorry. So this is for b dash. Let me just go down a little bit. So okay, if I understand this correctly, I might be wrong. So this should be also 0 because no, only the time coordinate changes in the case of b dash. Okay, so this is still 0. So I might have made a mistake there. So and then one do the same thing for b dash relative to the O frame, but now your x coordinate, because v is because O dash is actually moving relative to O, then you acquire this quantity which is given from the one from this it's going to be x equals to v. It's going to be x equals to v times this quantity, okay, which is actually that. Okay, so now what do we want to take all this general case is to get the relationship between the spatial coordinate in some sense. Let me go down here. So one of the things that we know is that the light signal will actually obey the equation of a sphere, if you remember previously. So I can now have this x coordinate over here corresponding to this light signal a dash p. Okay. So this light signal over here as measured by O will be given by this equation over here. Okay, so this will be the spatial coordinate with respect to x. Okay, and then square them, and then you have your y squared and z squared. So that will be the equation of sphere, and then this will be the time for which your signal is actually being emitted at a dash. Okay, so this is just like your c squared d squared equals to x squared plus y squared plus z squared, but now your x is going to change, your t is going to change. Okay, so you plug in the coordinates over here. Okay, and similarly for pb dash, which is another light signal. Okay, so and then you add in your time coordinates over here and your x coordinate over here, and you can see that the difference here is just your sign over here. Here is a minus, here is actually a plus. Okay, and with some algebra you need to take the difference between these two equations. Okay, so we're not going to do this here, so I'll leave this as an exercise for you to do the algebra. Take the difference between the two, then you'll be able to get this equation. Okay, your y squared and z squared will drop off, and you're left with this equation, for which you can simplify it to be equal to this equation. Okay. And finally, if we rearrange this equation properly, then we'll get the formula for the time coordinate. Okay. So again, one can look this from the point of view of O dash frame. Okay. So O dash frame, then your V is going to be substituted by minus V. So your reference O will have velocity minus V relative to O dash. Then again we do the same trick. Then you have your T time coordinate T for your O frame related to the time coordinate in O dash frame. Okay, and rearranging this. Again, I'm skipping a few things here. So you rearrange the one we had earlier for x to get an expression for x dash. Okay, so x dash is here. So you rearrange that, and essentially you get the other coordinate for your spatial coordinates. Sorry, I'm not prepared for this particular part because I didn't do the algebra properly before coming to this lecture. But I hope you can actually try to figure out how to get these equations out. Okay, and essentially what happens over here, you just simply has this idea of the coordinate transformation between O and O dash. Okay. All right. Now let's consider, instead of that one event just tells you how to do the coordinate transformation of x and t. Let's consider the case of a neighboring event p and q. So there's another event q. So again, the technique is just the same thing. What's the difference over here? You have this extra delta x, delta y, delta z, and also delta t for q in comparison for p. And similarly in the O dash frame, you have the same kind of thing. Now, why do we want to do this? Is to make to use the invariance of the light signal. Okay, and you consider the events P and Q connected by a light signal, and then you should be able to write this equals to this. Okay, and if you write this as a connection with the light signal, then this should be equal to 0, because the I've introduced that okay, never mind. So but the important thing, this one should be equals to that. Okay, and then once you have that, then you can use the fact that, okay, we can express this quantity delta x dash minus c squared delta t dash squared. Okay, and this is written in terms of the delta x and delta t over here. And then you'll be able to see that this is going to be related to your other coordinate in the other frame, which is related to that. And once you have that, then you'll be able to show that your delta y dash squared and delta delta z squared, okay, will be the same in both frames. And once you have that, then you can sort of parameterize what your how your y dash and z dash is correspond to your y and z. Okay, so we can think of as a degree of freedom involved over here, which amounts to a rotation. Okay, so meaning even though delta y squared and delta z squared are the same, okay, I still have this freedom of orienting the axis differently. Okay, so in other words, your y and z may point in a different direction compared to y dash and z dash. So that is just the main point over here. Okay, so but given this, you have this flexibility of rotation, so one can make them to coincide. So in other words, one can just simply take in this case theta to be equals to 0, okay, and then you get y dash equals to y and z dash equals to z. Okay, so finally, given that kind of orientation, then you'll be able to relate all your space-time coordinates in this manner between the two frames. Okay, right. And this relationship between this space-time coordinates is called Lorentz boost in the x direction. One could also do the same thing in different directions if you want to. Okay, this is just analyzing it with respect to the frame reference over here. Is moving with respect to the x coordinate only. Okay, so generally it can be more complicated than this, but here is what we call a frame just moving in the x direction, and then the coordinate transformation is just given by that. Given that we have oriented the y dash and z dash frame to be the same as y and z frame. Okay. In general, this could also have a different orientation if you want to. Okay. Right. Finally, one of the things that one should also notice is the fact that one can actually see this quantity of delta x squared plus delta y squared plus delta z squared minus c squared delta t squared should be the same. Okay, this is essentially just correspond to the light signal, so to speak. Okay. Oh yeah, now it should be clear that this is actually equals 0 because you are thinking in terms of light signal. Okay, so how far the light signal has gone in time will correspond to how far it propagates in space. But the point is, essentially, one has this invariance of this quantity in general. So if it's correspond to the light, this will actually equals to 0 for light. But in general, that interval between an event, okay, two neighboring events will have that quantity, and we call this quantity to be delta S squared, which might not be equal to 0, okay, in general case. That has to be invariant in both what we call O frame and O dash frame. Okay, I think that sort of finishes off there. Let's see. So I will give you some exercises later on, probably early next week, okay, to go through all this. So the next thing that we want to do is, let me just introduce this thing here. Is the idea of your space and time is not really independent of each other. Okay, that means one should consider all coordinates at the same time. Okay, so somehow your time coordinate is not really anything that you observe with respect to certain event is always having this time coordinate and space coordinate going to be somehow related to each other. Okay, and that relation is actually given by earlier quantity of this thing. Okay, so one has to treat space and time as a whole set of coordinates. Okay, and we can try to coordinate in the following way. Instead of writing x, y, z, and t, I will now use x1, x2, x3, and x4 will be the extra coordinate that we're going to put in, which represents the time. Okay, but in order for me to really treat them on equal terms, I actually want this to be of dimension distance as well. So there should be a c times d. Okay, so your fourth coordinate is going to be your time. Okay, and essentially the interval that we had earlier that has to be invariant is going to be the same in all inertial frames. So this is the same for all inertial frames. So this quantity is called a four-dimensional interval. Okay, and you can compare this with the case of the say Newtonian mechanics, where you had delta x squared plus delta y squared plus delta z squared, which is the what we call the length of delta s, if you want. Okay, square, and this will be the same in any other frames. So this is like your length of the vector square earlier. Sorry. So this squared interval is the case of Euclidean space that we had in classical mechanics, but now you have the same thing happening for the case of special relativity, where instead of just 3 spatial coordinates, you also include the time. Okay, and we're going to use this to define a metric. Okay, just like you had earlier. Let me just recall, you had this thing, for example, v squared is really vi delta ij vj, you remember? Okay, So this is essentially what we call the Euclidean metric. And we also have the same thing when you apply to this four-dimensional interval square thing. Okay, so how do we write this? We write it in almost the same way. Okay, but since we are talking about interval, I'm writing in terms of interval here. So I'm going to write delta x mu and then delta x nu, just like your vi and vj, and then there'll be another object which is relating to the square squared length in 4 dimensions, just like you have this squared length in 3 dimensions, related by this delta ij, which is corresponding to your Euclidean metric. But now you have a different thing which I write as eta. This is symbol eta. Okay, eta mu nu, where this eta mu nu has this particular matrix form. Your Euclidean metric previously was 1, 1, 1, and then 0 elsewhere. But now over here it's actually this 1, 1, 1, which is like your Euclidean metric before, but for time it has a minus 1. Where does it come from? It's this minus sign. Okay. So in other words, we have a non-trivial modification of this Euclidean metric, okay, with this called diagonal elements, okay, and this should give you the length square in 4-dimensional space-time, and that length square in 4-dimensional space-time is going to be invariant for any event. Okay, so this gives you a new geometry, just like this one gives you a geometry in classical mechanics given by a Euclidean geometry. So this now will give you a new geometry which is given what we call by the idea of Minkowski space-time. Okay, so your Minkowski space-time defines a new geometry that we need to write in this special relativity. So your eta here is sometimes called a Minkowski metric, just like your delta here is your Euclidean metric. Okay. Right. I have to also mention this. Different books will actually adopt different metric structure. Okay. The one that I employ here for this particular set of notes is I'm just making an extension to the four-dimensional space-time with this minus 1 appended to this 1, 1, 1 thing. Okay. There are other cases where you find other books use a different kind of metric. Okay. The different kind of metric is over here. You get 1, minus 1, minus 1, minus 1, where this 1 corresponds to your time, and this minus 1 corresponds to your space. Okay, and the way they coordinatize for this particular metric is that you have the 0 coordinate to be your time, and your 1, 2, 3 coordinate will be your x, y, z. So instead of x1, x2, x3, x4, where x4 is your time coordinate, the one that I adopted, now they use x0, x1, x2, x3. Okay, so be careful when you read different books. They can adopt different metric. In fact, there are even a different metric that looks like minus 1, 1, 1, 1. Okay, meaning it's similar to this coordinatization, but instead of x4 here, they put x0 in front just like this one, but your sign in your interval here, for example, so instead of this, I have minus delta x0 square in front and then plus with that. Okay, so you have to be careful when you read different books. Okay, and the four-dimensional interval for this metric, for example, will be given by this. Now, these are often used when they do particle physics. Okay, because why? The fact that your quantity here is supposed to be a square. Okay, so normally one expect that to be a positive number. Okay, and that means this thing is always bigger than that, which is always the case for the case of a particle with mass. It won't, the limiting speed will always be the velocity of light. Okay, so in other words, this has to be bigger than that for any particle which has speed less than speed of light. Okay. In our case, however, let me just tell you why this is a bit odd. Because over here, normally this will be bigger than this one. Okay, so in other words, for ordinary particles, this quantity is bigger than that, so essentially the sum of all this is going to be negative, and the negative doesn't seem to be a squared term in some sense. So in other words, this is not really used in particle physics, but some relativists use this because it's an extension of your Euclidean metric. So it's just a convention. Okay, so one has to remember that. Okay, so in other words, mine is probably, when it comes to a normal particle, I have my delta S squared to be negative instead of positive. Okay, so that's only the reason why. I hope this, I'm sorry about this fumbling of things done today because I was not really prepared. I had some other things on my mind. So probably I want to stop here and continue next week. Okay, maybe this is a good place to stop. Is that okay, everyone? Sorry for this fumbling. My mind is actually elsewhere. So let me take the attendance. Okay. So I'll stop for this lecture today, and then if there are any questions, please try to do the algebra, because there are a lot of algebraic steps that are sort of skip. Okay, and if you have questions, you can raise this in the WhatsApp group, or or email me or something like that. Okay. So I'll stop here. Thank you, everyone.
Thank you, Doctor.
Okay, sorry for the bad lecture today. Okay, bye.